in the U.S., and good evening to our friends in Europe. I'm Charlie Smith, Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and scale. The foundation of the G-PST is a group of 6 system operators from around the world who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. More information on the G-PST can be found at www.globalpst.org. ESIG serves as the lead of Pillar 1, and as such, I would like to welcome you to our monthly G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and will focus on the research agenda and research questions of Pillar 1. Topics will be presented by both the founding system operators and other advanced system operators active in Pillar 1, and members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST will also be provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to www.globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're going to be using the Slido platform at slido.com. We will not be using WebEx for questions. You need to open a browser window, go to slido.com, and enter ESIG10, ESIG10, as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote and help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar consists of a talk on developing an engineering framework to support Australia's energy transition. Based on the list of registrations, it looks like another very popular topic. The webinar will feature Christian Schaefer, General Manager of Energy Systems Engineering at the Australian Energy Market Operator, who is leading the charge in this area. In his role at AEMO, Christian leads the Energy Systems Engineering Department, providing engineering oversight to the transmission planning and design teams, power system incident root cause analysis, energy system integration analysis, and specialist engineering studies. I feel very fortunate to have Christian here with us today. He's a very active participant in both ESIG and the G-PST, and a good friend, and it's a pleasure working with him. The webinar today will describe AEMO's proposal for an engineering framework to provide an integrated roadmap for the national electricity market's energy transition. When we look back in history on this date, it will be remembered for 2 things. One is the 3-week anniversary of the Biden-Harris inauguration, and the other is Christian's webinar. Christian, no pressure or anything here. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG10 to ask your questions. And without any further ado, let's go ahead and get started. And Christian, I'll now turn it over to you.
Thank you, Charlie, for that very kind introduction, and a good morning, good afternoon, good evening to all of you listening in. Today's webinar, entitled Developing an Engineering Framework to Support Australia's Energy Transition, is intended to contribute to the discussions that the G-PST and the ESIG are championing on renewable integration and the decarbonisation of our electricity sector. And over the next 30 minutes, I'm hoping to introduce to you AEMO's proposal for an engineering strategy for Australia's national electricity market to identify the needs of our changing system to provide a platform to prioritise the most critical of these and to help inform and engage with all our stakeholders. The agenda of today is reasonably brief. I'm going to first contextualise some of the salient points of the Australian power system and AEMO's role within this, and to help frame some of the challenges and opportunities that we see in the road ahead. Next, I'll go back to where the framework development really began by reviewing some of the key findings of the renewable integration study of last year, after which we will then look at what happened in the 6 months since we published the first stage of the RIS, and the bulk of the presentation will then build on these preceding parts to introduce the intent of the engineering framework, what it is, what it isn't, and where in the transition we see the greatest needs. Before we then wrap up and briefly explore how this framework interacts and engages with the overall NEM reforms that are underway, as well as highlighting the timeline and how to get involved if you have thoughts and ideas on the framework. So let's get started. Well, Australia is a big place, and AEMO, the independent system operator and market operator of the NEM and the wholesale electricity market. Today we're going to focus on the East Coast, which is the national electricity market. And it's a network that stretches from the very far north of tropical Queensland all the way down to the centre of South Australia's outback, about 4,500 kilometres long, very dispersed and made up of 5 regional networks. Demand ranges from a summer peak of around about 35,000 megawatts, with shoulder period lows of about 14,000 megawatts. There is currently an installed generation capacity of about 57 gigawatts, of which currently 13 gigawatts is operational wind and solar, although there is about 3,500 megawatts currently in the process of construction, so those statistics will change slightly. Interestingly enough, 13,000 megawatts of rooftop solar has been installed in Australia, of which about 10,500 sits in the NEM. And in the 1920 financial year, distributed PV produced about 7% of the NEM's electricity requirements. On the other side, the NEM's coal-fired generation fleet provided about half of the generated electricity, while wind and solar made up around about 16%, with the balance then being provided by other sources such as hydro, gas, and so forth. The market structure of the NEM is an interesting one. It's an energy-only market with a 5-minute dispatch interval that is dispatched by AEMO according to demand forecasts. And AEMO also operates the national electricity market's total 8 regulation and contingency frequency control and ancillary service markets. And these energy and FCAS markets are co-optimized pre-dispatch by an economic dispatch engine that takes into consideration physical network constraints, demand, bids, and other economic factors. There is no ahead mechanism to the NEM's dispatch, and AEMO uses pre-dispatch forecasts to manage expected reserves for resource adequacy purposes. Operational forecasts are provided through AEMO's solar and wind forecasting systems, the ACIS and the AWIS, although AEMO has also been running self-forecasting trials for renewable generators in cooperation with the Australian Renewable Energy Agency over the past couple of years, and this is primarily to assist renewable generators to benefit from this and managing their cause of haste payments, which are penalties applied if you don't meet dispatch targets. The renewable integration study journey started back in late 2019 as the steady growth in renewable uptake at the time presented the question of just how much renewables can we put into the network and still operate securely, followed then by and what could we do to increase that level of penetration. About 6 months later, we then published the first stage of the RIS, and this slide summarises some of the key findings. Now, shown in the slide are historic renewable penetration levels projected towards 2025 under various development scenarios that have been taken from AEMO's National Transmission Planning document, the Integrated System Plan. The graphs plot the instantaneous penetration against demand, where each dot represents 1 half-hour period. The 3 scenarios illustrate grey as the actual instantaneous penetrations recorded during 2019. Red is for the 2025 projections of the central scenario, or in the OSP, business as usual case. And in orange, you can observe the predictions for the 2025 step change, which reflects both consumer and technology-led transition and a very aggressive global decarbonisation. Now, the 2019 figures show that most of the penetrations are less than 20%, and a maximum instantaneous value of just about 50. However, then looking forward, even under the business as usual scenario, we could see increasing periods of instantaneous penetration across the NEM of more than 50% and as much as 80%. And in case of aggressive decarbonisation, we could potentially see instantaneous penetration levels reach as much as 100%. However, there are, of course, challenges in operating at these levels, and the coloured areas underneath the scatter plots indicate our current awareness and predictions of the type of technical challenges that would have to be dealt with in order to permit such levels of penetration. In yellow, we see the increasing volumes of distributed PV that need to be managed for wind and solar penetrations and presenting issues with dispatchability of plant, predictability of behaviours of DER, as well as managing minimum demand levels. In light blue, we will start to see challenges appearing with managing the variability and uncertainty that must be considered when we have high levels of wind and solar participation in the dispatch, usually greater than 50%. My fault. The purple area then is bounded by a solid line that reflects our current understanding of the levels of penetration based upon our current understanding of limits as well as dispatch that we would likely be able to operate up to 75% of instantaneous penetration given the current system if we have the right operating mechanisms in place. Now, there are two key things to note about these plots, and that is that the potential impact due to the changing energy mix could present very significant challenges that we need to overcome, and that even in a 5-year step, we could see some fundamental changes occurring in the way that the NEM may need to be operating, and that places a time limit on how quickly we need to respond to these challenges. Now, the first of the changes that we have observed since we last published the RIS is shown here in this scatter plot, which contains the same 2019 half-hour intervals of instantaneous penetration as plotted against demand and the updated 2020 figures. Now you can see that instantaneous penetrations have increased by almost 10% or more, and that is visible in both the nose point of the curve or the scatter plots, which is your daytime penetrations, and the lower levels, the kind of kink in the step, which is really a nighttime. We're still analysing the details, but key contributors to this change are likely to be an increase of over 5 gigawatts of renewable generations being put into the system, that's both large scale and distributed, and a reduction in underlying demand, potentially also the outfall of the COVID pandemic, as well as the removal of constraints in certain parts of the transmission system that have seen existing renewable energy sources being able to operate at high levels. And it's worth noting, though, that even if the instantaneous penetration levels have been lifted, the limits that were outlined earlier at around 75% still remain and increase the urgency to plan for the needs of the system as we move forward. Something else that has occurred during the last 6 months, potentially world first, is the supply of all electricity demand of a large transmission system, in this case South Australia, using only 100% solar generated electricity. I do need to caveat that by saying that we did have 4 gas-fired generators remaining online at minimum dispatch levels to provide the necessary system strength and inertia, but these were not actually required for energy production. Remarkable is also that almost 80% of the electricity demand was provided by the roughly 1.5 gigawatts of rooftop solar installations located in the distribution system of South Australia. Now, the event occurred during a very balmy spring Sunday afternoon in October, when demand was reasonably low, and we also had some low wind speeds. That resulted in only a small contribution from the roughly 2,000 megawatts or so of installed large wind generation. The implications of the coincident high wind generation and the continuing surge in rooftop PV is going to continue challenging this renewable transition, and it is going to create some ongoing technical requirements to ensure secure operation. However, in other regions of the NEM, there's also been some significant developments, such as the 94% synchronous to non-synchronous generating levels in the National Electricity Market's southernmost region, that is the island state of Tasmania. Tasmania is connected to the mainland via a single line-commutated HVDC link, and it has substantial wind reserves of some very exceptional quality. For those who are familiar with the location of Tasmania, it sits right in the path of the very strong westerlies called the Roaring Forties. Tasmania is also blessed with exceptional hydropower opportunities, both run-of-the-river and storage, and many of these units are clutched and can operate as synchronous condensers to support the system without having to be generating power, which certainly has increased or helped to increase the SNSP levels. Solar generation is limited in Tasmania, being one of the southernmost states. Solar radiance is quite low, and currently solar installation in the state is limited to about 200 megawatts in distributed PV. There is also an economic assessment underway to duplicate the existing HVDC link, and this potential second link would pretty much double the DC capacity, and it would likely increase also then and encourage and incentivize installed wind generating capacity that could further see the SNSP levels increase to potentially regularly as close to 100%. The RIS then identified many of the challenges that are presented by the rapid uptake of large-scale and distributed renewable generation, the withdrawal and retirement of conventional generation in plant, changing consumer behaviour, as well as other exogenous factors. The observations and action plans of the first stage of the RIS triggered a proposal for a more holistic framework that would provide a holistic view of the changing needs of the system. It would also focus on the urgent operational needs and the longer-term infrastructure investment decision-making requirements. It would look to draw together the collective experience and expertise from across the industry to contribute to current processes and future priorities, and seek to link as many relevant system design and engineering focus areas as possible. More so, it's a piece of work based on communication to inform stakeholders, provide transparency, and convey how stakeholders can get engaged. So on reflection of the challenges observed and predicted, as I outlined earlier, we initially proposed an engineering framework that would be grown in 10 specific pillars, distributed across 3 central themes as shown here. The themes reflect the critical technical aspects of power system operability, which looks at the requirements of the control rooms, as well as the back office analytical support tools that would be needed. Secondly, the network architecture as an overall catchment of those aspects that have longer-term implementation timeframes or R&D components, which could substantially impact on the energy sector transition, and the successful integration and utilization of DER. Thirdly, then, the system services and qualities that include resource adequacy, frequency management, voltage and system strength management, and system restarting. The themes are all interlinked and they also overlap so that all of them support the success of the engineering framework, ensure the interoperability of the NEM across all of the projected long-term planning scenarios to envisage. Now, before stepping into specific areas in more detail, it's important to put into focus that this is a power system engineering framework. It's not intended to be a market design or energy policy strategy on its own. So let's maybe have a look at the system attributes theme that brings together processes and mechanisms that the system operator will need to manage essential services and maintain system security. Within this theme, we've proposed 5 pillars: resource adequacy, frequency management, voltage control, and system strength and system restoration. Resource adequacy relates to having an overall sufficient portfolio of energy resources to be able to achieve continuous real-time balancing of supply and demand, and the challenges in achieving success are reflected in the changing energy mix that we're seeing across the NEM with increasing variable generation, as well as the coincident displacement or retirement of conventional or dispatchable plant. Additionally, the variability in operational demand that is due to the uptake of solar PV, distributed solar PV, that is, will also have to be managed. And the engineering framework envisages that more accurate forecasting, increased visibility of available resources, and flexible energy sources will all be needed to manage this. The objectives of the frequency management pillar of the engineering framework is probably one of the most far-reaching in terms of operating the future power system, as the stable operation of system frequency will remain a fundamental requirement for some time to come, even as we do increase the uptake of inverter-based resources. And a more granular overview of the short-term frequency work program that AEMO is pursuing here was published by us in late 2020, and you can find this on our website. But essentially, the focus is on NEM critical issues of incentivizing primary frequency control, which was only mandated through a rule change back last year on a 3-year trial basis. We need to also establish minimum inertia levels to operate the system. We're also looking to define the fast frequency response services arrangements and the effectiveness and need for emergency frequency control systems. Supporting all of these would be an effective ancillary services arrangement, such as being considered right now by Australia's Energy Security Board and the Market Commission, as well as having appropriate tools to manage system frequency. Now, we're not just talking about operational decision-making tools, but importantly, the accurate analytical tools that are used to detect threats and risks early and to respond to these. Voltage management is similarly a large catchment of stuff that includes both the static and dynamic voltage control. It also goes beyond the simple management of voltage at the transmission level, and it needs to explore more deeply planning at the transmission and distribution interface, particularly given that we're seeing so much growth in DER, as well as the continuing and increasing decentralization of the generation fleet. System strength is also going to continue to challenge us, particularly as this decreases and creates more complex scenarios to operate wind and solar generation in. And already in Australia, we've seen a lack of system strength manifesting in unstable inverter-based resource control system interactions, as well as unsuccessful poor ride-through of wind farms. So it's no longer an uncertainty, but a critical system issue that we're going to have to manage. Now, system restoration used to be something that was planned for but rarely used. Unfortunately, in the history of the NEM, there's only been very few statewide blackouts, the most recent obviously being the 2016 blackout of South Australia. However, the NEM system restart services are all currently provided by self-starting or synchronizing from household thermal and hydro generators. And this will naturally create challenges in a power system with few of these times left. And we really need to start thinking about how we can restart the network using other means. The current procurement process for services that is underway and inviting tenders is, however, going to most likely result in very similar services that we've had in the past, being made up of, say, self-starting or synchronizing from household plant. Moving on then, I think we'll recognise that the power system operates 24 hours a day, every single day of the year. And the NEM is all overseen from the AEMO control rooms and those of the regional transmission and distribution businesses. And as our electricity system evolves and transitions, pretty much every aspect of power system operation will be affected in some way. And consequently, we are going to have to consider the changing needs of the control rooms and the back offices. And within the engineering framework, we currently foresee that there's only 2 key objectives for system operability from this viewpoint, and that is ensuring that the control room tools are fit for purpose in advance of being needed, and to establish visibility and high-speed data recording to support both real-time decision-making as well as offline analysis. Now, the first point is not only about identifying the key operational decision-making tools that are going to be critical, but also to ensure that they are operable and can integrate well with existing other tools that we currently have. And ideally, the control room will have to be adaptable and able to respond to rapidly changing system conditions, as well as being able to predict events based and observe changing conditions in time to initiate control actions. So that at its core, this pillar is developing the control room capability to manage the power system of the future. And just to help an example, some of the activities that fall into this area that AEMO is currently pursuing is the establishment of NEM wide area monitoring systems and high-speed data collection at a much more granular level, the improved visualization tools to aid our operator response and decision-making, and even pilot projects such as real-time inertial measurements to be able to quantify some of the things that are going to become critical for us to view. We all know that successful power system operation is also about preparation. And hence, in addition to our control room, we are going to need to be able to analyse and assess the power system using computer simulation to be able to identify threats ahead of time. And the system analysis work that we're conducting is therefore dependent on adequate modelling and analysis processes that will continue to improve the accuracy and veracity of the power system model using said real-time wide area measurements and information that are fit for purpose and agile enough to adapt to the changing conditions as we change our generation mix and as demand varies, and to create accessibility to the same power system model for all participants. So creating a single source of truth, so to speak. To give examples of what I mean here, there's a number of initiatives that AEMO has progressed within this area, including the development of wide area EMT models to accurately model system strength, establishing common sources of information, initiating feasibility investigations for an EMT-based real-time simulator, and establishing a ESIG power system modelling sharing platform. AEMO will continue to engage with industry to report progress and updates. We're also seeking feedback and input on other opportunities. Now, decarbonisation is not just about building more solar or wind generation and retiring thermal plant. It's also not just about operationalisation of what we already have, but it's about the organic and coordinated development of the power system capability. And that makes integration potentially one of the more complex things because it involves such a wide range of affected parties, reflect uncertainty about the rate and the depth of technology and the innovation therein, and not least is bounded by economic and potential costs to end consumers, and therefore of some interest. Of the pillars listed, distributed energy resources is by far one of the most significant challenges to manage, but it's also an area with some of the greatest potential opportunities. And key matters that AEMO is looking to pursue and consider in this area include observability, because DER is currently not visible to AEMO, the predictability, because of unknown or unexpected behaviours of distributed solar PV to frequency and voltage disturbances, for example, and the last lines of defence, that is, under frequency load shedding, because operational demand is offset by DER and therefore removes that capability. To assist with progress in this work, we've been engaging very extensively within this scope, including partnering in virtual power plant pilot projects, investigating the potential for provision of ancillary services from small-scale battery storage systems, and to revise the technical standards of AS4777, which is the Australian equivalent of 1547 IEEE standard. Moving on then to the next topic, power system resilience, as we've defined it, is the ability to limit the extent, the severity and duration of system degradation that follows an extreme event, whether that be man-made or natural. And we see it as an inherent characteristic of the power system that can be designed and built during the planning phase, and I do apologise for that, during the planning phase, and that is enhanced and is expanded during the operational time frame. And the work that we're doing within this area is really looking to establish acceptable standards and metrics for power system resilience. And the key work here is to establish these and explore the ones that can be used to measure and to establish acceptable performances for these, balancing these obviously against costs. And then lastly, we're also looking to exploit innovations that technology can bring. And we propose to keep abreast of opportunities we have by engaging closely with organisations such as the Australian Renewable Energy Agency to understand new technologies being trialled, to work collaboratively with vendors and equipment manufacturers to understand their technology, and to support technology trials wherever possible and not in conflict, obviously, with our responsibilities. We also propose to continue to engage internationally with our peer organisations and engineering bodies to maintain awareness. And similarly, we're also looking to engage collaboratively with the broader industry as we see technology innovation as a significant part of areas that are critical to our success in areas such as new generation technologies or inverter-based resources, communications and measurements, grid support, artificial intelligence, and many more. This will be important as many of these technologies will be needed not just to solve the problems we're working on right now, but also those that we have yet to observe as we continue to integrate more renewables. Coming to a close, and I wanted to have a quick look at how this engineering framework sits within other activities. And in addition to ongoing NEM-wide operational and planning activities and publications that the engineering framework will influence and be influenced by, there is also foreseen to be an engagement with the NEM's regulatory process. And this slide shows our view on the linkages between the Energy Security Board, the Australian Energy Market Commission and AEMO to develop the future system design. Now the AMC, or the Australian Energy Market Commission, is the rulemaking body of the national electricity market, while the ESG is the Council of Australian Government's appointed board that coordinates the implementation of security reform blueprints that were commissioned by these guys in 2016. And more specifically, the ESB, working with other market bodies, is responsible for the post-2025 NEM reforms or the market reforms, and the AMC is responsible for the detailed design and implementation of the national electricity rules that govern both market and system operation of the national electricity market. The green pathway shows the ongoing ESB work that advises on the long-term fit-for-purpose market framework, and it's being progressed through, as I said before, the 2025 market design, which you'll find the details on their website. Similarly, shown in the blue pathways, some of the activities of the Market Commission, and the AMC is receiving regularly several rule changes that relate to the ESB's program of works, which will then be used to act on recommendations coming out of that program. Three parallel pathways of the ESB, the AMC, and the engineering framework indicate or give an indication of the interaction between the processes and how in the current transition we're working as an industry, building on each other's work plans and developing market and regulatory frameworks in a way that's grounded in very solid and up-to-date technical advice. The interaction between all of these is interdependent and complementary in a way that the engineering framework provides some detailed mapping between individual projects and activities, such as indicated in the purple arrows and lines, and in this way the technical needs of the power system can help to contribute to the consolidated and holistic system and market design of the future. So what's in store then for the time ahead? The timeline that is shown here indicates where we've come from, and we published a consultation paper back in December last year, and it gave some time then for that to be reviewed by industry, and then met in a virtual workshop in February to seek feedback from the broader industry that we can then let flow into the draft publication that we're looking to publish in March. Now, the submissions on that draft publication will then be due in April before we publish the final document in June of next year to help inform said processes and build a roadmap forward. Once that has been published, there will be regular and ongoing updates to this document as the needs are changing, as technology changes, and as the system conditions change. If you would like more information on any of this, you can check it out on AEMO's website, and that's www.aemo.com.au. And you can also email the Future Energy Systems team at futureenergy@aemo.com.au if you would like some more information. Now that concludes the presentation. I hope that it stimulated your interest and thinking.
Thank you very much, Christian. It certainly did. Before we jump into the Slido questions, I'd like to ask a general sort of question, give you a chance to maybe give a little bit of context to your effort here. I think it's fair to say that a lot of eyes around the world are on AEMO, very much aware of the significant challenges that are coming at you very rapidly. Just curious, from an international point of view, what kind of interaction have you had with other system operators that are concerned about similar things, or what kind of cooperation is going on? Are you kind of doing this on your own, or are you in touch with other folks? What's the sort of context to this?
No, look, absolutely. I think that this isn't a unique challenge. I mean, electrons don't know borders. And I think that the laws of physics apply in Australia just as they do in other parts of the world. And the engagements that we've had, particularly through the Global Power System Transformation Consortium, which involves 6 of the system operators that are experiencing some of the greatest transition, as well as through ESIG, we have had close collaboration with an exchange of ideas, particularly in areas of control and tools and the sort of things that we require, as well as in operational forecasting. AEMO has been very proactive in this space and utilized machine learning techniques for probabilistic forecasting in the operational time frame. So there's been a flow of information between system operators, such as our colleagues at EirGrid, at ERCOT, as well as CASO, National Grid, and so forth, and contributing to as well as learning from this, which is a very important component of what we're doing.
Thank you. That's great. There's a couple of questions here that look pretty popular, so let's jump into them. One from Christian Zur. What is the main limit underpinning the solid blue line on the right of slide 4? Voltage, transients, frequency stability. I think that was the far right line, if I recall correctly.
That is correct. The slide that was shown was the scatter plots of the predicted or potential renewable penetrations, and the solid blue line that was on the far right hand side is the current foreseeable limit to operation that we currently predict based on the minimum number of synchronous generators that we foresee will be online. It's a limit that is then driven by system strength to maintain stable and solid voltages, as well as sufficient inertia in the system to prevent catastrophic runaway rate of changes of frequency and so forth. So it's a technical limit based on our current understanding of the forecast minimum synchronous generating levels.
Okay, thank you. The next question is kind of related to that from Phil Creveld. IBRs are phase-lock loop-based grid following, and therefore frequency instability will occur as IBR penetration increases. How do you expect to solve this?
It's a very good question. For those of you who may follow some of the developments in the national electricity markets, this is the very issue that we had to wrestle with in the region of the national electricity market we refer to as the Western Murray Zone. It's an area that borders New South Wales and Victoria, and there is a lot of solar generation located in this area, as well as some wind. It is quite remote to the larger nodes of synchronous generation and therefore low system strength. And in this low system strength area, we had observed unstable oscillatory interaction between control systems when there were minor disturbances in the system, line switching and so forth, which triggers that oscillatory instability. The solutions that were implemented were the tuning of the control systems of the PLLs of a number of solar farms. So there is an approach to wide area tuning of phase lock loops, as well as some adjustment to the structures of those control systems to reduce the adverse interaction. At the same time, you do need to anchor and underpin the system strength in the network, and by inserting some sources of system strength, in this case synchronous condensers, we're able to raise the system strength to sufficient levels to operate the network stably. Obviously, that was a solution for a particular area, but it's a concept that would be able to be applied to other areas as well. Similarly, in South Australia, we've had an issue with lower system strength, for which reason we have to maintain a minimum number of synchronous generators, because without these units providing system strength, the low system strength and fault levels in that region can create problems with fault ride-through and transient voltage recovery of some of those wind farms, which can lead to instability. So there's ongoing challenges for both converter-based resource PLLs that would need to be managed through a combination of control system tuning and conventional sources, as well as in other parts of men for wind.
Okay. Just a follow-up question from myself on that, Christian. You showed the slide of South Australia with the day where you hit 100%, and I think you said you had 4 synchronous machines left on. Were those 4 synchronous machines providing that frequency response capability or the inertial response that you were just talking about?
That's right. So we had, for security reasons, have to dispatch a minimum number of 4 synchronous units in South Australia. By the middle of the year, though, we are planning to commission, or the South Australian system owner or network owner, Electronet, will be commissioning 4 synchronous condensers, which will then allow us to review the need for operating that many and potentially reduce the number of synchronous generators we'll need online. So there will be some ongoing changes.
Just for those on the line, I would also say that that's one of the top questions that the G-PST is dealing with in its research agenda. So it's a very pressing question for all of the system operators that are facing this in the not too distant future. Kind of related question from Mark O'Malley, Christian. In your definition of SNSP, is that the same as air grids? And if so, how do you explain a 90% value? At least that's what he thinks he saw on the slide. I do recall it was kind of a high value, and I think that air grid has operated, a few years ago, I think they had like a 50 or 60%, and I think they're up to 75% now with incremental changes. So I think that's what Mark is comparing it to.
Absolutely. The figure was actually 94%, and it's exactly the same calculation that air grid uses. It's the total amount of wind generation and your HVDC imports in relation to demand and HVDC exports. The comment that I made earlier is that there is a lot of hydro generation in Tasmania that can operate as synchronous condensers. So you do have system support which allows you to provide you or supply your demand using imports and wind while utilizing hydropower to balance your network, and allows you to get up to those sort of high levels.
Okay. I guess a couple of related questions here from Wong Tong on engineering registration. First, a comment that engineering registration to ensure appropriately qualified and experienced engineers are making decisions for their areas of expertise in virtual environments is important, or are there such qualifications? And then a related one just a little bit further down. A key component of RES integration is secure design, and does the engineering framework take into consider this requirement, for example, engineering registration? So I guess it's a question about engineering registration and how that factors into your way of working there in the engineering department.
I'm assuming that engineering registration is about achieving chartered and registered status. We've always had a requirement, certainly in Queensland, for some time to have a registered status, particularly for engineers that are involved in signing off on construction and so forth. Victoria has also included or introduced legislation to make it mandatory to recognise the need for professional and registered engineers. And I would foresee that other states will follow, so that you are creating a level of understanding that can be recognised in capability. And the process for registration obviously is one that showcases a journey of understanding and expertise in particular areas. So yes, I think there is a need to show registration and qualifications, but at the same time, a practitioner that's got 25 years of commissioning power plants but hasn't had a registration should not be someone who will be disqualified or barred from it. So there should be a recognition of skills and capability as well. That's my thought. Okay.
Question here, kind of a detailed question on slide 6. Was utility solar curtailed on October 11th?
No, it wasn't. So AEMO does not have the ability to curtail the distribution level solar generation.
Okay. Question on resilience. What kind of resilience metrics are you currently considering, and what are the specific units of measurement? I don't know if you're there yet, but that's an interesting question anyway.
There's a lot of work being done throughout the world on saying what are appropriate metrics for resilience. Is it outage rates of thermal plant and conventional generation? Is it outages of transmission network elements? Is it the recovery time to bring lines back in? AEMO is currently working through trying to identify what those are. Internationally, there's a number of other organisations that are doing similar work in trying to identify what are reasonable and measurable metrics and what is an acceptable level for performance of the power system. So we're not at the point yet where we would conclusively recommend or seek to discuss it, but through this process, we will look to explore what is reasonable to put in for those, and certainly working closely also with the ANC on those matters.
I think that's another area of active investigation around the world. Here's a question on market design, Christian. Do you see the need to overhaul the NEM design in order to cater for this change? The NEM-DE is to optimize energy price, not system strength or inertia needs.
It's a good question. Certainly, I'm a volts and amps guy rather than an economic designer of market systems, but I am aware that certainly the ESD's post-2025 design, in the ANC's great work on system services that we might need, is looking at everything from how would you incentivize primary frequency response, how would you create potentially a structure for fast frequency response. Is there a place for a head mechanism for dispatch? These are all questions that the market will need to address, certainly as we move forward. And the slide I showed earlier with challenges to system strength, frequency control, as well as the variability and uncertainty that will impact our dispatch, are all going to be things that we will need to have the right services in place for as we continue to increase renewable penetration.
Okay, another popular topic of discussion throughout the world, and I think that a lot of people are talking about the same thing, recognizing the same issues coming up. Given the requirement for real-time data, what do you consider to be real-time? Seconds, milliseconds, or microseconds, and synchronized across the entire grid?
There's a few things underway currently, and certainly AEMO consultation with and collaboration with the network service providers or the network owners is working to expand both the granularity of the conventional or SCADA-based 4-second cycle collection time data, as well as high-speed triggers and monitors that can provide on a millisecond basis. But we're also looking to increase the number of installations of PMUs or phase measurement units in order to collect information that is more relevant and critical to system strength calculations and so forth, where phase angles are of primary importance. So the work currently going on is, first of all, the expansion on granularity by installing more SCADA-based high-speed monitoring equipment, as well as the increasing installations of PMUs to include then further measurement data. With the granularity that is for SCADA 4 seconds, for the high-speed stuff in the millisecond time frame.
Okay, and one on DER. Can you speak to AEMO's approach towards DER controls, distributed energy resource management systems, etc., and in which cases direct control is required versus passive control?
Look, I'll need to take it on notice and provide some information back, but I can say that AEMO has been involved in a number of technology trials for virtual power plants, where we're looking to marshal distribution level battery storage systems to provide ancillary services or FCAS kind of services. But these are installations of those sort of sub 6 megawatt trials at this point in time in South Australia. But certainly I can provide some more information on those.
Okay. And this looks like a follow-up question to the earlier one on curtailment from Mark O'Malley. I assume that if you did not curtail rooftop solar in the 100% example, you did curtail utility scale solar and wind.
So yeah, look, that's correct. We didn't curtail the distribution level solar, but you would have had to manage transmission level solar and wind. If you look at whatever the operational demand is, South Australia also has a limit on how much you can export, and that export plus operational demand would set the limit to what you can dispatch on the transmission system, from which you would then need to take away the minimum dispatch for the synchronous generators that were there for security. At the time, though, there wasn't that much wind. There was some curtailment, and South Australia does not as yet have extensive large-scale solar, although it is certainly growing. So yes, transmission level renewables would have to be constrained at certain times, depending on the export capacity and underlying operational demand.
Okay. Let's see. Am I on?
Yes.
Yeah. Okay. So, question on the other side of the fence, Christian, from Russ Stolbrick. What efforts are being pursued to adapt consumer behavior to align with availability of wind and solar?
Good question. Look, I'm not that familiar with tariff structures that might be being used by retailers in Australia. Certainly in Australia, when it does get hot, people want to run their air conditioners. Being incentivized to switch it off or turn it down is probably not something that most people would necessarily consider. However, during emergency crises, when there is a predicted shortfall in reserves, there are mechanisms in place to have voluntary restrictions and curtailments, and under extreme conditions there may need to be some mandatory restrictions considered as well. So the incentives probably sit more on the retail side of things rather than with the AEMO system operator.
Okay, and a kind of a follow-up question from Russ. If you can't control rooftop solar, what will you do when you exhaust controls and export capabilities? Well,
this is where it becomes quite a challenge. The interconnect between states facilitate the transfer of power, but all to a particular limit based on the security of transfers. So operational demand, which is already predicted to reach zero, so this is the demand seen from the transmission system, by, say, the mid-20s in South Australia. If that were the case, you obviously will need to start curtailing your transmission level generation according to what you can export. So you're still in a lot of wind, still in a lot of solar, and you also need to operate synchronous generation for stability, which is why we're putting in synchronous condensers to reduce the number of synchronous generation that we need to have online and facilitate more renewable generation in that state. The market mechanisms that currently exist will look at balancing supply and demand, as well as managing the security. So the mechanisms that are in place right now will continue to the point where maybe constraints will become quite significant in terms of lost opportunity and energy.
Okay. I'm going to go to this one on the engineering framework. How specific is the engineering framework going to be with regards to the 5 areas of system needs? Will it introduce new services with clear technical specs? Another active question.
The engineering framework is intended to identify the needs and provide input to the market reforms and market designs. It certainly highlights the need that we have for system strength support, for frequency, for inertia, as well as other such mechanisms. So it's looking to provide input and to help our, rule makers and policy makers to have good technical advice on hand to be able to design them in a way that form follows function, to be able to make decisions on what is the most efficient and economic way to deliver those services based on the technical requirements.
Okay, let me jump down to the bottom and ask a question related to the previous one. And that was from Julian. Is the use of the SNSP metric, does it apply when there's such a high penetration of inverter-based rooftop solar? I haven't thought about that one before.
It does apply, I would think, in that you're looking at renewable generation on the transmission system and underlying demand, and the demand itself is obviously being offset by distributed solar PV. And Tasmania, we talked about before, DPV is quite low, so those numbers we do align more with what we see in other regional countries. But as we move forward, it still comes down to what demand you have. So whether you take native demand, i.e. what is actually being demanded by consumers, or whether you offset that and have a reduced transmission generated renewable fleet providing the energy, the numbers will still align, I would think.
Okay, let's take this one on cyber. Does the framework consider cybersecurity issues and resilience in the operation of the NEM?
Well, a great question. Certainly, resilience is looking at not just changing weather patterns and phenomena, floods, storms, convective downbursts, and all those sort of things, but it's also looking to increasingly consider cybersecurity aspects of it, or the man-made threats, or eventually even terrorism and damaging of infrastructure. I think it needs to consider all of those aspects. And certainly, AEMO is quite active in looking into this, and certainly the Department of Home Affairs in Australia has also taken these kind of threats very seriously. So resilience will certainly consider cybersecurity and threats that might result from those to the power system.
Okay, I think we've probably got time for one more question. Here's one of general interest, I think. Has AEMO started to look into grid forming technology or PSCAD or PSSE studies proactively?
Yes, so we have been engaging with, and may be aware that the Australian Renewable Energy Agency has been very supportive in exploring and supporting the potential for grid forming technologies. There are a number of pilot projects that are being considered and looked at, and AEMO has been speaking to ARENA as well as some of the developers of this technology directly. There are some studies, first of all, looking at how grid forming technology would perform. It is a research and development area at the moment for us to consider how this would perform. I think that there are some OEMs that say it is already feasible and realisable. For example, the F3 battery sitting in South Australia has, according to ABB, already got the potential to operate in a grid forming mode. However, that is currently when it's islanded, and when it's synchronized to the system, it does still grid follow. So the technology is already growing. It is starting to become more mature. AEMO is engaging in some of the activities around this with ARENA subsidised and supported projects, as well as on the international level. ESIG, for example, is very proactive in this space, and we are looking to contribute and engage in this side of things as well. In terms of PSCAD and PSSE studies, that really is the foundational and cornerstone to do your development and to look at what can possibly be done before you then develop pilots and demonstration projects.
Okay, I'm going to ask you one last question, general question that's not on here that's been on my mind, Christian. That's on transmission. We didn't say much about transmission in the engineering framework. Just curious how the transmission infrastructure development is going in Australia and how critical you see that to being helping to solve the issues going forward.
It's an excellent question. There's a couple of things around that. Let's say that there is an absolute need to optimize the utilization of existing infrastructure. There's also a need to optimize the design and build of future infrastructure. And particularly in Australia, we are, and the Integrated System Plan is looking at renewable energy zones, which are areas of high renewable resources, where the aggregation and collection of a large amount of renewables could be facilitated more easily through optimized infrastructure. The challenge for us currently, though, to build that stuff is in that the regulatory process that needs to be followed, which looks at the cost benefit of building infrastructure that will be paid for by consumers, can be quite challenging based upon the inputs that it currently takes. So, long story short, I think yes, we will have to build infrastructure, but it has to be selected and optimized, as well as taking advantage of existing transmission networks.
Okay, we were just a little over the top of the hour, so we're going to need to wrap it up. Christian, thank you for a very educational and informative presentation and for all the answers to the questions. I think we got to just about all of them. As I mentioned earlier, an email will go out once the video file has been posted. I also want to encourage you to send any remaining follow-up questions to info@esig.energy, and we'll get them answered and posted as soon as we can. We appreciate your engagement and look forward to seeing you again at our next webinar in this series, which will be held on March 10th at 4 p.m. Eastern. Nick Miller of Hickory Ledge and Matt Richwine of Telos Energy will be speaking on the topic of grid-forming inverters and power export stability. We hope you'll be able to join us once again. Further information on all the webinars can be found on our website, esig.energy, under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Christian, I want to thank you once again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you again in March. In the meantime, everyone, take care, stay safe, and thanks again for your participation.